The molar mass of an element gives us a link between the mass of a sample of the element and the amount of atoms that is in that sample. And this is really important because if you want to go into the lab and you want to do a reaction, you want to say, I need to add 2.5 moles of sulfur to my reaction, you can't go and count out those atoms until you get to the correct number. All you can do is weigh them. And so you need this link between the mass of stuff that you weigh out and the amount of stuff in that sample that you've weighed out. And so we get this formula, which is probably the key piece of math that you're going to have to know. If you can't use this formula in your sleep, then at some point it's all going to come apart for you, right? And so we can say that the amount in moles of stuff in your sample, which is given the symbol N, little n for amount, is equal to the mass of stuff divided by the molar mass of the stuff. So amount is equal to mass divided by molar mass, or if you like, N is equal to little m over big M. You must know this formula. And this is what I say. We'll give you the constants, but you should assume you won't get the formulas, so you must know this one. Right? This one you do sit and memorize tonight over a whiskey. Yeah? Some people like triangles. Indeed, it seems to be that it's in the high school notes now that you do triangles. I should probably do this. This is probably more helpful. Do we know about triangles? Do we like triangles? Yeah? So here's the triangle. If you don't know about the triangle, then... Right? So you can do this sort of thing. And the triangles are kind of helpful because not only do you need to know that the formula says that amount is equal to mass divided by molar mass, but you also need to know that mass is equal to amount times molar mass, and that molar mass is equal to mass divided by amount. Right? You need to not only know the formula that way, but you need to know it other ways as well. If you like triangles, then that is okay. I have come to be a bit accepting of triangles. But let me point out to you that indeed, well, in the course of Chem 191, you will have to know this formula and be able to use it. Yeah? That's more tricky to put in a triangle. So you cannot be too reliant on the triangles, because the triangles give you a little shortcut for knowing how to do the rearranging, but they're no use here. At some point you do just have to stump up and learn how to rearrange an equation. Okay? And that's kind of about as a part, short of knowing how to use your calculator, rearranging equations is about as much math as we need you to be able to do in first semester chemistry, right? But it is enough that it scares a lot of people. If I say rearrange that for EA, so make EA the subject of that equation, could we do this? Sir?
Can you spell solver?
Sorry?
Can you spell solver?
Yes. Yes, we may as well rant about that while I'm here as well. Yes, chemistry has no requirements about particular types of calculators that you use. If you are doing first year health science, and many of you are, then you'll be doing physics 191. Yes? Physics. Physics require that you use a university approved calculator, of which there are like 3. And I am not sure whether they are one of these ones where you can just plug it all in and push go. You will need to check that out. If I know the guys who run the physics paper, and I do quite well, my guess is that they won't be calculators that can do that, because they're very big on expecting you to be able to do math, which is possibly isn't unreasonable for physicists. I've heard one of them say to me, if you can't do differential calculus, you can't call yourself a scientist, which is kind of a shame because I can't do that. But they will very much expect you to be able to do that stuff on paper, if not in your head. So yes, you can use them. I personally would still much prefer that you knew what you were doing rather than just making it yet another black box that you just believe the number that it mindlessly gives back. Because see, the thing with calculators, and not everybody knows this, is that calculators have different modes on the top. Do we know this? Yeah? Do you know what the different modes are? Do you know that if you do the same calculation but within the wrong mode, it will give you a completely different answer? And you have to know whether the answer is right or not. You know, I had this great argument with a guy in labs once. He told me that the sine of 1 was 0.86. I said, no, it's not. He said, yes, it is. He said, no, it's not. He said, look, I'll show you. I said, no, it's wrong. And it's because he had it on the wrong mode. Yeah? And he didn't know that sine of 1 is 0. Now, that's not going to be, we don't really do trig, so it's not going to be a big drama normally. But it just makes the point that the calculator is only going to give you the right answer if you know how to use it properly. So, long story short, in chemistry you probably can just plug all that into a calculator and get the answer out. But I would prefer it if you knew how to do it on paper as well. Just in cases, you know, your batteries might go flat or whatever. So, there is my little rant about algebra. It's important that you can kind of do some algebra. If this is all a bit new and scary, I do have a book full of problems about how to do algebra on your calculator. You know, how to do algebra with answers, and sort of taking you step by step how to use your calculator, not just plugging the whole thing in and pushing go. Even though there is there's level 1 putting everything in your calculator and pushing go now, isn't there? Yeah? How many people did that rather than actual math? Some people. Yeah, see. I'm getting old. Never mind. Moving on. Right, so how do we use this little formula? Well, this is the sort of the absolute most basic sort of calculation we can ask you to do. Imagine that we have 5.2 grams of carbon. And I say to you, if you have a sample of 5.2 grams of carbon, tell me what amount of carbon atoms are in there. What is the number of carbon atoms that are in there in moles? Then you would use your little formula. You would write amount is equal to mass over molar mass, and then if you like you could write it out again, specifically for the problem, so the amount of carbon is equal to the mass of carbon over the molar mass of carbon. You would put in your mass, 5.2 grams, which we give you in the problem. You would put in the molar mass, which we would either give you or you could find on the periodic table. And so they've made that 12.0. Sometimes you can make it 12.01, because that's kind of what it says on the periodic table. And you could work out that the answer is 0.433 moles. So there's a little bit less than half a mole of carbon atoms in a sample that weighs 5.2 grams. And then there's a little bit more mathsy stuff at the bottom there. It says, note how the G's cancel out, leaving the unit of the answer is 1 over moles to the minus 1, which equals moles. Maybe this is pushing some people too far. Hello?
Are we to do the moles to 3dp?
Oh, do you want to write brackets 3dp, close brackets after it? Please don't do that. It just makes my colleagues just titter.
That doesn't matter, like, can we do it to 2dp, or is it meant to be 3dp?
In this course, and in Chem 191, with the exception of one lab, we do not care. Right? We have bigger things to worry about, to be fair. But there is one lab where we make a bit of a deal about uncertainties and sig figs and decimal places and all that sort of jazz, right? So in the lab manual that you get for 191, in the back, and there's an appendix in the back that takes you through all this, the stuff that obviously you've already come across. And so strictly, that answer should be 0.43, yeah? Because the 5.2 is 2 sig figs, and the 12.0 is 3 sig figs, so the answer has to be the same as the smallest number of sig figs and the numbers you're putting in. There's a whole bunch of rules around all of this, but by and large, we don't care in first semester, right? So if you do 3 sig figs or 2 decimal places, that's normally what I would do, unless I had good reason to want to do it properly. That will be fine, right? The thing which you should be aware of, though, is that if you ask someone, like my friend here, who's all about believing everything his calculator tells him, and you write down 0.4331614771159, because that's what it said, then you will be harassed mercilessly by me and by my colleagues for being so silly. Right? You do not need to write out every single number that your calculator produces. 3 sig figs or 2 decimal places is normally fine. You can do slight modifications on that, but don't just mindlessly write out every number the calculator says, because that's kind of telling me you don't really know for yourself. You're just believing the little box. Yeah. This business across the bottom about the g's cancelling out, the way that we get the number in the answer is by taking 5.2 and dividing it by 12. Yeah, you're okay with that. The way we get the unit of our answer is by taking the unit of the 5.2 and dividing it by the unit of the 12. So grams divided by grams per mole. So this is algebra again. But if you take grams and divide it by grams per mole, then the grams cancel out. And what you're left with is the unit of the answer as 1 over per mole, and 1 over per mole, using these sorts of ideas we talked about here, is the same as just moles. If you're good at algebra, then doing this sort of thing is a way to get around having to remember the formulas. You can just look at the units of the numbers going into the calculation, and you can work out what you have to do in order to get an answer with the unit you want. Right? So if you take grams and multiply it grams by grams per mole, you won't get an answer in moles. So that must be wrong. If you take a number in grams and divide it by a number in grams per mole, you get an answer in moles. So that must be the correct way to do the calculation. Yeah? So if you're good at algebra, you can do that. If you're not, or I'm just starting to hurt your head, then just forget I said that. Yeah? Hello? So which one? This one here? That just means per mole. If you like, that's 1 over moles. It's like 1 over x, and that just means that undoes itself. Yep? Okay. So here's another one. If we said if you have a sample of 24.3 grams of selenium, what amount of selenium atoms are there in 24.3 grams of selenium? Then you would go to the periodic table and you would find out that the molar mass, the mass of 1 mole of selenium, is 78.96 grams. So the molar mass is 78.96 grams per mole. And again, you just use a little formula. The amount of selenium is the mass divided by the molar mass. 24.3 grams divided by 78.96 grams per mole, and that's 0.308 moles, with the correct number of sig figs this time, just randomly. Okay, we're happy with this? Hopefully this isn't too bad. I believe there'll be a bunch of these to do in the tutorial, just to bed it all in, if this is something which is... Now see, when I was using the laptop yesterday, the laptop's got this cool thing where you can see the next slide, but now I'm using this, and I'm sure this does it, but it doesn't do it automatically, so I don't know what's next, so I won't sound nearly so professional and organised today. Right. We're good with that? Yep. Whoop. Okay. So both of those examples involved using elements or using atoms, for which you can just look up the molar mass on the periodic table. We have to be able to do the same sorts of calculations with molecules. And of course you can't look up the molar mass of a molecule on the periodic table. That's not what it's about. But what you can do is you can look up the molar masses of the constituent elements in the molecule, and then you just add all those together to get the molar mass of the molecule. So, imagine we wanted to work out the amount of sodium chloride that was in a 1 gram sample of sodium chloride. We have to work out the molar mass, and so to work out the molar mass of sodium chloride, we just find the molar mass of sodium and the molar mass of chlorine, and we add those together. Yeah? And those will both be on the periodic table. You might go, but it's not sodium and chlorine, it's Na plus and Cl minus, which is true, but remember we said yesterday that the mass of an electron is only about 1/2000th of the mass of a proton. And so a sodium has got, what is sodium? 11. So it's got 11 protons in the nucleus, and then we're taking 1 electron away. So the change in the mass of the atom on going from sodium to sodium plus is going to be very, very small. Not enough that it's going to matter for our calculation. Yeah? Hello?
What about if they're like chlorine, like 2 atoms of chlorine? It's not in that one.
And say MgCl2.
Yeah.
Yep.
You just times the chlorine, the molar mass times the
Absolutely. Yep. It's just the sum of all the masses of all the stuff in the molecule. Yeah. And so if we just add the molar mass of sodium to the molar mass of chlorine, we can work out that the molar mass of sodium chloride is 58.44 grams per mole, and then we just do our calculation as before. Yeah? So long as you've got the formula, then you can work out the molar mass. And then there's one to try. Maybe get this down and I can flick back to the slide if you need. Calculate the amount of CO2 gas in 53.9 grams of the gas. Mass of CO2, and so to do that it's going to be the molar mass of carbon plus 2 times the molar mass of oxygen. So carbon's 12, oxygen's 16, so 2 16s are 32 plus 12 is 44. Yeah? See, I did that without the calculator. So 44 is the molar mass of CO2. And so to work out the amount is just going to be the mass, which is 53.9 grams, divided by 44 grams per mole. And that will come out as being 1.2 something. What is it? 1.225. Yeah? Do we all get that? Cool.